All right, so we are starting a new chapter today, linear quadratic regulator. I don't have a PowerPoint for this one, but I have a very nicely written chapter. This is chapter 7 of my book. You will be able to see the book in about 6 weeks to about 2 months from now from Springer. This is chapter 7 of that. So it is about optimal control, right? Which means how to control a plant with minimum resources. Okay, it can be minimum time, minimum energy, minimum error, like that. So in this area, one of the very popular controllers is linear quadratic regulator, right? Now we will first discuss what is called the finite time linear quadratic regulator, which means, okay, there is a regulator and we want it to regulate the plant in a fixed time. So we give it a time, like in exam, you get 3 hours to finish it. Okay, whether you do it or not is separate matter, but 3 hours is the time. So finite time control. Then the regulator means, you already know this, but let me tell it again. Regulators try to bring all of the state variables to zero, right? Everything kept at zero. If you deflect it, one or many of the state variables from zero, immediately it will create, if you will see the deflection or disturbance, whatever it is, and try to bring that down to zero, right? So that is what the regulator is doing. But you might think that, okay, then what is the use of this regulator in a wide spectrum of applications, right? Because not every application is a regulator problem, right? There are tracking problems also. They are the controller has to track a reference. But the thing is, regulator can be redefined as a tracking controller also. Only thing you need to do is, right, before you send the disturbance, right, at that whatever tracking level that you want, or whatever level you want the controller track, then in opposite polarity, of course, then the regulator will try to bring the state variable to the desired value, because you are deducting the value. Let's say you when you input the signal to the regulator, you deduct 1 unit. Then the controller sees, okay, I am -1. So it tries to move it to +1 so that it will see 0 as in actual value is 1. So this simple technique will allow you to use a regulator as a tracking controller also. Okay, right, fine. Now, what is our plan? Equation 7.1 is a plan. Everybody knows about it. Continuous time, state space model. Okay, so there shouldn't be any question about it at this moment. When we talk about optimal controls, we need to have something to optimize. Okay, so what are we going to optimize? Think about it. So you need to have this objective function 7.2. You have to write it down. Okay, so I would write it like this. Most of the books in optimal controls, you will see similar or same expression. Right? It is very long, but this is what happens when you use mathematics as a language to write a simple thing. Right? This could have been written in plain English in one short sentence. But if you want to write it mathematically, it becomes like this. So if I break down this one, K is the cost, the total cost of this control, okay, is half XTF transpose PTF XTF. which means TF means the final time. Okay, so our time horizon is 0 to TF. So TF is at the end of the process. X is the state. So this is a state at the end, state at the end. So if it goes to 0, this is 0, this is 0, and the whole thing is 0. That is the best scenario. Okay, at the end of the time, all of the states would go to 0. Perfect. But if it is not the case, it is a cost. It is a cost. Okay, so that is why we include it like that. And of course, I think you know this format, right? Xt is a column vector. Xt transpose is a row vector. So when you multiply the same state vector, row and column, you will multiply element wise. So every state becomes square of that value. So this is the square sum. This is the square sum of all of the states. That is why you call it energy, right? How much of energy is there at the end? And what is the function of PTF in the middle, this one? Well, you can have it a diagonal matrix. Each element says how important that particular state is. Some states have a higher cost than some other states. So you can put higher value for those states and low value for the other states. In order for you to adjust it, we have this PTF. So this is the final cost. But before you get there from 0 to TF, this entire time duration, there is a cost. So you can see the same expression over here. This is the cost of all of the states, running cost, right? This is the control cost. Every moment there's a control signal, right? If it is just one control signal, you just get the square. In that case, R is just a number. But if you have more than one controls, then it's a vector, and you need to have the same structure as of the states. So this first part over here is the running cost, the running cost. Plus, this is maybe new to you. If you haven't studied about optimization, this is completely new to you. When we do the optimization, we are not actually free to optimize everything, okay, the way we want. We are not free to change any state freely, right? Disregarding other state variables. They're all connected through the dynamics of equation 7.1. 7.1 says how things are connected. So this is a connected system, not a free variables. If they were all free variables, you can find out the best combination to reduce the cost. But unfortunately here, it's not the case. They are connected. So you need to do optimization without disturbing this system connection. So that's why we bring it over here. System connection, that is x dot t, right? Or you can say ATXT plus BUT minus x dot t. This whole thing should be 0, right? If it is not 0, then there's a cost because you are violating, you're trying to violate a constraint. Okay. So this is strictly enforced using this lambda transpose. We call it Lagrange multiplier in the cost. Okay. So as long as there's no such violation, you don't need to have this. Okay. If there's no violation of the system dynamics, if everything works according to the system dynamics, right, there's no need of this one. Okay. Now we need to optimize this cost J. How do we do that? So to do that in LQR design, we do this. We define something called Hamiltonian. Hamiltonian H, which is equal to L plus lambda transpose F, right? So in fact, in this particular case, this is the Hamiltonian, right? So if you go back to 7.1, you will see it is part of the cost function itself. You can see this is the running cost. This is the system dynamics. Okay. So you combine these two together, running cost and system dynamics. This part over here without the integration, right? This is the constrained uh, running cost. Okay. We give it a name like Hamiltonian. Okay. Again, this goes back to the standard optimization theory where you have Lagrangian and then Hamiltonian to find out optimality of a system, right? So LQR comes on top of that. So that is why certain things are actually probably new to you, right? Now we have this Hamiltonian. We know that this is the running cost subject to system dynamics, okay, constant. And then S is the first part, right? We define this as S, capital S. This is the final cost, okay? Clear? This one and this one. So the complete cost is actually J and S combined together. And H has to be integrated because it's from 0 to TF, whereas S is only at the uh, end time. Now, there's a necessary condition for optimal controls. There's a necessary condition for optimal controls. Again, in the Hamiltonian theory, it is derived, but here you can use it as it is. The condition, the necessary condition, the condition that has to be satisfied if you have optimal controls is this. The partial derivative of the Hamiltonian, right, with respect to the control u is 0. Okay. Now we have the Hamiltonian, and this is not part of u. It doesn't depend on u. This depends on u, and here also you have u. So only these terms with respect to u, right, is this half RU star plus R transpose U star plus B transpose lambda. So B transpose lambda. Okay. And here U transpose R. Okay. So this is the condition for optimality. And because this is not a general thing, but just specific to optimal controls, we put this star sign, not just U, but U star, to say that this is the optimal control. Okay, this is the optimal control. We need to find out some equation we can use to calculate the optimal control at that moment of time. Right? This is our problem now. How can I find an equation which I can use to calculate the optimal control at this moment? Okay, and Hamiltonian says differentiate the Hamiltonian with respect to the control. Okay, and Hamiltonian is the cost with respect to you. Of course, you can understand this one, right? If you want to minimize if you want to have optimal controls, you need to minimize the cost with respect to the control. Everybody understand that? So this is one of the conditions. And we know that R is a symmetric matrix. So therefore, R and R transpose are equal. If you have a symmetric matrix, if you get the transpose, will still be the same. So therefore, there's no R transpose. It is just R. So that this becomes just RU star. There's no half. They're added together. And there you are. You can get this equation. 7.5. U star is equal to minus R inverse B transpose lambda star. This is your optimal controller, right? Similar to PID controls, for example. In PID also, you have UPID, PID control signal is equal to some equation, right? Proportional derivative integral gains. Here in LQR design, finite time, this is the optimal control signal. But the problem is, now if you look at R, do we know R? Yes, I know. Do I know B? Yes, I know that. Do I know lambda? No, I don't. That's the problem. You cannot calculate optimal control without knowing the Lagrange multiplier. So therefore, we have to wait a little bit. Okay. Now, in the optimization theory, Hamiltonian, right, there's another condition which says lambda dot is equal to minus the gradient of the Hamiltonian with respect to the state, right? This is another condition for optimality. We use this one to calculate lambda actually, and then we can put it over here in 7.5 and calculate U star, the optimal controls. So if you differentiate H with respect to X, you get this one, right? Keep your note aside because otherwise I will have to go up and down many a time, right? So you can have a look at all of these. If you have a printout, so much the better, so that you can go to these numbers when I refer it over here in the text from 6.34. Of course, you don't have 6.34. I only shared chapter 7. I'm sorry about that. But I have written it over here, literally, right? 6.34 says this one. Rate of change of the Lagrange multiplier in the optimal setting is equal to negative partial h over partial x. So you go to h now. H is this one. Differentiate with respect to the state x. So then you get something from this term. You get something from this term, right? All the other two terms, they don't depend on x. So they're not part of this equation. So you get this one, which is equal to 0. Again, you know Q is diagonal, so that Q and Q transpose are equal. So you can add these two together as just QX minus A transpose lambda star. This is the optimal lambda. So it is a dynamic equation. Like it's not just an algebraic equation, it's a dynamic equation of this nature. Rate of change of lambda is equal to minus qx minus A transpose lambda, 7.6. And in Hamiltonian optimization, right, it's a process that goes from start to end. It has boundary conditions. You want to substitute boundary conditions to these equations, right? If you want to find out the exact values, okay? So some equations start from time 0 as boundary condition. Some equations start at time t, endpoint as the boundary condition. And you know the values there, you can substitute to this some of these differential equations. Then you can calculate the equation backwards. So you know how we use the initial condition and end conditions, right, in differential equations. So the general boundary condition, 6.37 again, that this has been derived earlier. It says that if you look at the final cost S, right, of the system, S is over here, this one. right? Final cost, okay, endpoint, and differentiate with respect to x minus the Lagrange multiplier transpose is equal to 0. This is a condition, boundary condition, with delta TF is equal to 0. So you have finite time. TF means the final time. Delta TF is any deflection there. No, you don't have any deflection. Like exam has 3 hours, full stop. So at that point, it ends. So when you have final time fixed, we say it like this. Delta TF is equal to 0. So this is to say that the final time is fixed. This is finite time control. The finite time control. This is one of the requirements. So there are cases infinite time control, which means final time is not fixed. Don't misunderstand that. Infinite time doesn't mean that it is actually infinitely long. It only says final time is not fixed. So the system can stabilize in a second, in a minute, in a day, in a year, or it might never settle. So all these scenarios are like included in the infinite time word. Okay, right? It's not necessarily very long time. Okay, so don't take it as a little meaning. Take it contextually. So now when you differentiate S with respect to S, you get this one. This is lambda transpose and TF. You can see this one. This condition is valid at n time, TF. Okay, this is only applicable to finite time control. And from that one, you can get this equation, 7.6. So what does that mean? At the endpoint, right, the Lagrange multiplier is calculated this way, right? You have your final time, whether it is final state, 0 or otherwise, whatever it is, take that value, right? And multiply with the PTF. This is the process state cost at the end point, and that is your Lagrange multiplier value at TF. Then you can put it over here and calculate the rate of change and calculate all of the state variables, the Lagrange multipliers, their values towards 0. You can run the algorithm. Okay. Now, I want to show how we can close the loop here as a feedback, right? So, so you take this as your boundary condition, right? And you can write it for every state, right? You can see it here. The boundary condition 7.7 shows that the terminal state cost weight actually, PTF, relates the final optimal state, right, to the final optimal core state. So this is what's called the core state. Lambda Lagrange multiply is also called core state. So this final state cost relate final state to final core state. Okay. So let's assume that the same relationship exists for any time t as follows. So if you look at any other time between 0 to TF, you can write down this expression, assuming that this condition that is true at time TF is also applicable for any time from 0 to TF, okay, along the optimal trajectory. This is just one unique trajectory, optimal trajectory. So when you use this one in optimal control law, where is that? Here, 7.5. You can replace your lambda star, the core state. Okay. This is actually time. I have not written time here. These are continuous time. Okay. So u is actually ut, lambda is actually lambda t. Okay. So for any time t, the optimal control is given by this equation. Can you see that? This is the optimal trajectory xt for any particular optimal state of the optimal trajectory at any moment, any time between 0 and tf. If you know the state, you can put it over here and calculate optimal control. So when you have the optimal control, right, you have the optimal trajectory, you have the optimal Lagrange multiplier. So everything is optimal. Okay, because optimality is just one single scenario here. So state variables, control signal, state variables, that is lambda, yeah, in the optimal setup, they all get this star sign. Now, if you put equation 7.9 is the control signal back to 7.1, which is the system dynamics. Okay, this one, system dynamics. Take ut out, right, and put the optimal controls in. Then you are making your system optimal system. All what you need to do is take ut out and put u star t in. Okay, so when you do that, what happens? You get this equation. Okay, so this is the this is a feedback loop, because when you have this is very much, this looks similar to x dot t equals ax, isn't it? So it is running system. X dot on the left hand side is equal to something times x. So this is what is called the optimal state dynamics. So now you can see A is a system matrix, right? It is constant. The moment system is given, it is fixed. B is also fixed. R is the cost given to the control, right? The control cost. P is the cost given to the endpoint, right? Final point cost. If you go back and you can see that here, this is PTF, final cost. You can give that, but all of the other costs, right, you don't know. How can you do that? Without that, it's not complete, right? So for that, what we do is this. To determine PT is the issue now. For every T, you have to determine P. Okay. So we get 7.8. That is this equation. Equation for the core state. We differentiate it. So when you differentiate it, it becomes like this. P dot x star, P x dot star. Okay. So coming from 7.8, this one. When you differentiate a product, u dv plus v du, like that. Okay. You differentiate one and keep the other one unchanged and do the opposite and then add them together. So differentiation of a product. Then you substitute for lambda dot from 7.6 and x dot from 7.1. So you're going to substitute for x dot and lambda dot. So lambda dot on the left, x dot on the right. You're going to substitute. So this is what you get for lambda dot. You have this earlier, 7.6. And for x dot, you have this one. X dot equals ax plus bu, of course, right? But now because it is star, we have to write stars for controls and the state. Then you substitute from 7.8. Substitute from 7.8 for lambda star. Now what you do is you remove lambda star, right? So when you do that, you can see lambda star in 7.8. Lambda star is px. So you bring it over here, right? This lambda star goes away and px star comes in. And from 7.5 for u star, so 7.5 u star means r inverse b transpose lambda. So you can see here r inverse b transpose lambda. Now on one side you substitute for lambda, on the other side you substitute for u. When you do that, lambda comes in, right? So then you again remove this lambda using 7.8, same way that you did here, px star. So px star comes over here. Okay, it's kind of going back and forth kind of thing, but it's important. Otherwise, it will be complete chaos, right? If you want to do it in one stroke, it's not going to happen. Now, eventually, we got rid of lambda. Now, there's no lambda anymore. There's no u anymore, right? Of course, you have x, the state, but every term has x. X star, x star, x star, x star, x star. It is a common factor and you can take it out. When you do that, you get q, a transpose p, p dot, pa, pb r inverse, b transpose p. And you can arrange in this way. So on the left-hand side, it is the p dot, rate of change. On the right-hand side, it is just an algebraic expression. These are all matrices. And because of the dot rate of change is a differential equation. This is a matrix equation as well as a differential equation, both at the same time. So we call it a differential or matrix differential equation. Okay, maybe first time you see this kind of thing. It's a matrix equation because A, B, and everything matrices, vectors and matrices. And there's a rate of change of one matrix here, P dot, because therefore it is a differential equation also. So therefore we call it matrix differential equation. And the person who first studied this kind of thing is Riccati, way back, a mathematician, I think from Greek or something. So therefore we call this kind of equations wherever it appears as a Riccati equation. Okay, so Riccati equation is a very abstract, generic thing in mathematics, where mathematics is applied, especially in controls. When you see a differential matrix equation, right, we call it a Riccati equation. So it's not easy to solve Riccati equations, right? You need to use MATLAB and other software platforms to solve Riccati equation. When you solve the Riccati equation, you can find out P. Okay, so if you have P, game over, right? When you have P, you can calculate U star, optimal controls. Okay, for any time t. Right. Any questions up to now? Now let's look at the nature of the optimal cost, because when you do the optimization, um, what you say is, okay, my gradient is 0, something like that, the first order necessary conditions, right? But you can have the gradient 0 for minimum or maximum. Okay, so therefore you need to go to the next derivative or the second derivative and figure out whether you have a minima or maximum, right? So that is the discussion over here, nature of the optimal cost. Um, so now if you recall 7.6, let's see it over here. I have to pedal back and forth quite a bit. So this is the differential equation for the co-state. Okay, co-state. It's the Lagrange multiplier that we use to fix the cost with the constraint. Another word for that is co-state. It looks like somewhat similar to the state. So over here. So this is our co-state equation. Then you can rearrange it with A transpose lambda star on the left hand side. And then you know that Q is a symmetric matrix, so Q transpose is equal to Q. So you can write it like that. Let's say 7.12. And then from 7.9 and 7.8, right? So 7.8 and 9, if you pedal back, these are the two equations, right? 7.8 lambda star, the optimal co-state, and optimal controls. So using these two equations, right, you can write this one. U star T is equal to minus R inverse B transpose lambda star. So I think you can refer to this equation and how this is fixed together, okay, to reduce going back and forth. So then it follows through, eventually get Lagrange multiplier, the co-state transpose B is equal to minus U star transpose R, because R is again a symmetric matrix. You know why R and Q are symmetric? Because Q is the weightage of the state energy. So each state has a different value for the energy. So the Q matrix has all these values along the diagonal. So is the R. If you have more than one control input, each input has a certain energy. They may not be the same, okay? So it's a diagonal matrix. Along the diagonal, you have these values fixed. So you have 712 and 713. So the two terms lambda transpose A and lambda transpose B. Here you have lambda transpose A. Here you have lambda transpose B. In the cost 7.2 are replaced by the two equivalent expressions derived in 7.12 and 7.30. So why we derive 7.12 and 7.13, right, is that to have these two statements, lambda transpose A and lambda transpose B here, right, um, um, to replace the same terms in the cost 7.2. So if you look at 7.2, you can pedal back over here, right? You can see lambda transpose A, right? and also lambda transpose B over here. Okay, so it's a constraint basically. So you can replace these two terms in the cost. So when you do that, you can write it like that. This is the cost written again without time, simple t, because otherwise it would be more longer equation. Now you don't have A transpose, lambda transpose A and lambda transpose B. So in place you have this one for lambda transpose A and this one for lambda transpose B. I think so. Yeah. U transpose R. Yes, this one. So this is lambda transpose B. So this is the cost. In fact, this is the optimal cost because now we are taking the substitutions from the optimal process. So therefore, the cost is also getting optimal now. Okay. So that is why this star coming up over here. This is the optimal cost. Now the thing is, it's not a, even though it's called optimal cost, it's not a single number, right? It's not a single number because you can see this is integration 0 to TF. Okay, it depends on TF. So whether it is a very small time or a medium time or a long time. So depending on that, the cost changes. But for a given interval, it's a constant. Okay, for a given period, it's constant. But now think of your control process. It goes from time 0 to time 10, for example, 10-second control window, right? When you start at time 0, you know that you have to go for 10 seconds, right? You can compute the cost for the 10 seconds. Now, let's say you are halfway. 5 seconds has already lapsed. You have another 5 seconds to go. Now, if you don't worry about the energy you spend for the first 5 seconds, now you can calculate from 5 seconds to 10 seconds, right? 5 to 10. And that gives you a different cost. Okay. So the cost means the total cost, right, for that duration. So this integration tells you that. So the first term x transpose p x star transpose px star, right? This is the terminal cost. If the final state is not 0, right? There's an error. Error is a cost. We consider any error as a cost. Okay. Then you can simplify this one. I think some of the terms cancel out. Can see here x transpose qx, x transpose qx. See that these terms cancel out, right? And u transpose ru, u transpose ru, that also cancel out, right? So leaving u with these two terms cancel out, you are only left with lambda dot transpose x plus u transpose x dot, this one. Okay. Now the cost expression reduces its size, its length. Then you have a half here integration. If you look at this one, it's very nice expression, isn't it? You have lambda dot x and lambda x dot. So what about transpose? So it says you that this is a result of a differentiation of a product, and this is that product, lambda transpose x. So lambda transpose x is the product, and when it has been differentiated, that's why you get this expression. So lambda dot x, lambda dot x. So therefore, this is integration differentiation cancel out, leaving you lambda transpose x from T0 to Tf. So when you substitute the limits, you substitute the upper limit first and then the lower limit, right? Don't have to worry about in between, right? End and the start. Calculate the value there, calculate the value here, deduct. You get the entire difference, okay? So then I can write this one for Tf like this, half x transpose px Tf at time Tf and plus half x transpose px at time T0, initial time. Okay. And then you can see that the first two terms cancel out, right? This is actually the terminal cost, and so is this one, the terminal cost. They cancel out, leaving you only the initial cost. This is a fantastic finding, right? If you have optimal controls uh, to reduce, which reduces a certain objective function, right? When I say optimal control, it's not unique, right? It depends on your objective function, what you select as your objective function. So if I give you the same example for two students, their optimal controls could be different because the way they formulate their cost is not identical, right? Cost is not a unique thing that everybody writes the same equation of. It's very much subjective, okay? So therefore, there can be many different optimal controls. They're all optimal within that framework, okay? So whatever it is, your initial value for the cost function j, right, is the minimum cost. Is the minimum cost. So from here, it's very evident. But how can we get our heads around this expression? Half x transpose px at time 0. So initially, maybe there's error, right? State variables, they are not all 0. Some are 0, some are non-zero. So you can get the non-zero ones and get the squares of that and multiply with the respective p value, right? The weight of energy, the state energy, right? So this says that, okay, this is the total cost, right, of the entire operation within that time period, whatever it is. You don't have to spend more. So when you go from time 0 to time tf, this reduces. This reduces and eventually at the end, it becomes 0. If it goes to 0, so this is the minimum cost in finite time optimal control with the cost defined in quadratic form as given in 7.2, right? So this is not universally applicable. This is only applicable if you have defined your cost function quadratic as we have done in equation 7.2, okay, for quadratic. But remember, quadratic is a very common thing because any variable square is energy. We know that, okay? So this indicates a very significant fact. The minimum cost of the entire regulation process within T0 to Tf solely depends on the initial state, right? The cost depends on initial state, actually. If you have a large deflection, so it's a big energy, big cost. You know that, no? In a way, this is, now you understand, yeah, it is the case, okay? But before that, you didn't have probably um, an idea that it is the case, right? It could be the case. But now you understand whatever initial deflection, whatever it is, right? If you don't want to spend energy unnecessarily, right? The minimum cost that you would incur, right? It depends on initial error. So if it is a small error, small energy, small cost, big error, big cost. So hence it could be deducted that the minimum cost to go, there you are, cost to go. Have you heard that term? Cost to go means, okay, from here onwards, what is the cost? From here onwards, right? You started somewhere, now you have come up to a certain point. From here onwards, right? What is the cost to go? So that is what is given in this expression actually. So any time t, you can calculate that. So when you go to tf, right, you will see x is getting smaller and smaller and smaller. At the end point, it would be the minimum cost. Okay, I mean cost to go, not the minimum cost. Minimum cost means for the entire period, right? The total cost. But when you approach your endpoint, your cost to go reduces. Cost to go reduces, and eventually, if you go to zero, cost to go is zero there. Now, this concept of cost to go is the principle that is used by Richard Bellman in the celebrated dynamic programming. You may have heard this one, dynamic programming in optimization. Uh, it is based on this cost to go, where you have, say there are a number of cities, right? Say Colombo, Kandy, Trinco, Jaffna, like that. And somebody has to travel to all these cities, right? And maybe finally he has to go to Jaffna. So there are a number of ways to get there. So you explore these paths. So you figure out cost to go. If you go to Kandy, what is the cost to go from Kandy to Jaffna? If you go to, say, Mana, what is the cost to go from Mana to Jaffna? So you always work on cost to go and eventually find out the minimum cost. So that is basically the dynamic program. Now we have naturally come up with some mathematical proof of that same principle. Right, now let's look at the design process. How we can bring all these equations and eventually cook something, right, that we can actually make use of. So it says this, if you want to design a LQR, right, these are the steps. First one, solve the matrix differential Ricard equation using A, B, C, D, and R, and the final state cost weight, PTF. You have to calculate PDF by solving the matrix Riccardi differential equation, and for that you need to use MATLAB and math, like basic math software, right? Mathematica, MATLAB. Then you can calculate PD for the entire duration, starting from the end point. All of the P's can be calculated. So once you have P, you can calculate X star. So this one, the state trajectory, entire state trajectory, right? How state 1 changes, how state 2 changes, 3 changes, all of the states can be, the trajectories can be pre-computed, can be pre-computed. Not only that, you can use this equation to calculate control signals you have to give at each and every point. So as a continuous profile, this is my control signal, this is my state 1, this is my state 2, this is my state 3, like that. You can pre-compute everything. So the optimal controls that we discuss up to now is offline. It's offline. If you know the plant, you know the cost, you can actually pre-compute everything. So therefore, it's not a feedback control. It's not. It's a feed forward kind of thing. You can pre-compute everything, and then starting at time zero, you can keep giving the optimal control curve, right? So let's say if it's a straight line, for example, right? Say you are controlling a motor. So your optimal controls here is like starting PWM 50 to 150, right? In a matter of 5 seconds, 50 to 150. So you slew it up to that point, right? In 5 seconds, 150 PW. And you assume the motor position, speed, acceleration, everything follow that predefined lines so that the motor eventually gets to a certain point. Okay, something like that. But for whatever reason, your model is not perfect. Your matrix A, matrix B, they don't represent actual reality there. Your actual states will not follow uh, uh, the pre-computed states. That is the problem of pre-computing things, because the reality is always different, at least slightly, from your model. So therefore, you will end up with errors. You will not get exactly what you have pre-computed, right? Is that clear to everybody? Okay, so now we know many things about this optimal controls subject to a certain objective function. Okay, and we know that it is pre-computed profiles for state trajectories, for co-state, lambda. Sometimes you don't have to worry about lambda so much, particularly control signal. Okay, so when you pre-compute it, you will know where the control signal goes, whether this is pre-computation, you don't, there's no risk at all. You can see whether the control signal hits its limit, actuator limit. In that case, you can extend the time, TF, right, by another couple of seconds and do it again. Then you will see when you extend time, the control signal now doesn't rise as much, okay? And therefore you can keep it under the limits. All right, so this is not a online control thing, right? This is pre-computation. So you know everything, uh, even with a little error there, right? Because you know the offline calculations and the real life result are not the same. There are errors, but you can get some idea. Okay, so where it is, rather than right having no idea at all and trying to control something. This is much better. Okay, so the nature of the LQR optimality is, as I said earlier, you need to get the Hessian of the Hamiltonian. Okay, now you have heard of Jacobian. Jacobian is the matrix of first derivatives, first partial derivatives, rather. Okay, and Hessian is the matrix of second partial derivatives. Okay, you get the Jacobian and then Hessian. So you need this to say whether your optimum point is actually a minimum or a maximum. So what you do is you can get the second derivative of the Hamiltonian with respect to x, and you get this one, right? Half q plus q transpose equal to q. Uh, Q is symmetric. Uh, so then this is the second set, partial x, partial u. Then third one, partial u, partial x. The fourth one, partial u square, right? So when you have x and u, you have to get the partial derivatives of all the combinations, okay? And then you can actually generate the Hessian, right? That is the Hessian of matrix H, right? This is the first element, second, third, and fourth. So like that. So so it will be QR on the main diagonal and off diagonal zeros, right? So Q is a matrix, diagonal matrix. R is also a diagonal matrix. All the non-diagonal elements are zeros. So the purpose of the two matrices Q and R is to calculate the instantaneous cost of the state xt and control U. Hence, they are assumed to be symmetric and positive definite, right? I think you remember positive definiteness of a matrix. It says that when you use this matrix to combine x of two variables, right, to get energy of a variable, right? So it's a positive energy. It doesn't give you negative energy, right? So that is the very nature of Q and R. So when Q, which is a diagonal matrix, which is positive definite, and R, also diagonal matrix, a positive definite, then this whole thing is a positive definite matrix. Okay. The Hessian matrix is also a positive definite. The Hessian matrix is also positive definite. Sorry about this mistake. Write it down. 770. So we just simply say that greater than zero. When you say a matrix is greater than zero, it means it's positive definite. Okay. This assures the minimum cost under LQR control. So when you have the second derivative positive, you know it's minimum cost. So you have not gone to maximum, right? Right. Now it's time for us to see an example. So here is our system. X dot is equal to 0, 1, minus 1, 2, x1, x2, 0, 1, u, right? I think everybody is familiar with the state space model now. Now, let's define a cost function, okay, what we want to minimize through the control process. And that is J. This is the final cost, right? If the states after initial deflection don't go to zero, but end up having some non-zero values, how much of a cost is it? So this term explains that, right? We have two states. Get the first state square, second state square, but get 3 times of the second state square. And then get first and second states multiplied and twice of that. So these numbers are coming from somewhere, right? Without knowing exactly what the application is, we can't say anything about this number other than saying, okay, there should be some numbers representing the actual realistic cost of these terms. Okay, right. So plus this is the running cost given. Okay, right. Consider initial state x0, and this is the initial state. And 8 second is our time window. This is a 8-second finite time linear quadratic regulation. Okay, so this is how questions come to you, right? You have the plant, you have generated your cost function, right? You have the initial condition, initial deflection, 2 and minus 1. Now, when you start the controller, what it does is it will try to bring this 2 to 0, minus 1 to 0 within 8 seconds. So because we have not considered control bounds, okay, control signal cannot go beyond this level or cannot reduce beyond this level. There's no such thing. So therefore, this is unbounded or unconstrained control C. Right. So this is how we synthesize the solution. The plant starts with 2 and -1, the two state variables, and the optimal control is expected to regulate it, that is to bring the state to 0, 0 within the fixed finite time of 8 seconds while minimizing the cost. Okay, this is a complete description. The given system dynamics reveal the system matrix. You can see it over here, system dynamics. It reveals the system matrix. This is A and B, right? A and B. The cost function is arranged as follows. So you can actually write the cost function as the state transpose P matrix and the state, the standard quadratic form, remember? So when you do that, it becomes like this. This is the same expression that you have here. Can you see that? You have x1 square, 2x1, x2, 3x2 square. So check that out. Here, when you multiply, what will happen? You get x1 square, 3 times x2 square, right? And 2 times x1, x2. But by writing this way, we figure out that this is the P matrix at final time. This is the P matrix at final time, remember? Okay. So P is varying. It's not a constant. This is the value at the end point. Because P comes from a Picard equation, differential matrix equation. So there's a P dot, rate of change. This is the final value of that matrix. And then half integration xt transpose, right? The cost, this one, can be arranged in the similar manner up to this point rather. And then single control input 0.5 u square. So this is a Q matrix for the two state variables plus ut transpose 0.5 ut, right? This is actually R. So from that reformatting, we can calculate PTF as this matrix, Q is this matrix, R is just 0.5. Now, when you know all these matrices, A, B, Q, and R, right? From here, A, B, then over here, Q and R. This is P, but it's not a constant. All the other things are constants. Then you can put these matrices into this equation, matrix Picard equation. On the left-hand side, you have rate of change of all 4 elements of the P matrix. And on the right-hand side, you have P matrix in multiple places together with A, B, and R. Okay. So now you can write down 4 equations when you actually multiply the right-hand side, right? It becomes like 2 by 2 matrix, long matrix. Then you can write down the equations. Okay, element 1, 1 equal to element 1, 1 on the right-hand side. Element 1, 2 is equal to element 1, 2 on the right-hand side. Like that, 4 equations like this. Okay. But actually, P matrix is also a symmetric matrix, right? Therefore, the off-diagonal elements are equal. So P12 is equal to P21. So P12 dot P21 dot you look at these two, right? So they are same. And the first value at the endpoint is known, right? And off diagonal values at the endpoint are known. And the value of the last element in P matrix at the final time is also known, right? Because this is a PTF, which is known. Okay, this one, this is PTF. Don't get it confused as a constant matrix. It's not. These values are at the final time. But before that, the values at any point, right, must be calculated using these differential matrix equations. Right. So you can use the MATLAB code given in appendix, solves these three differential equations and calculates the optimal control 7.9. So once you solve the differential equation, you can get the values entire range, okay, from 0 to TF. When you have P, you can calculate the states, the controls, and everything. You can done the pre-computation. Right? And these are those trajectories. For X1, I think starts with 2, and in 8 seconds it goes to 0 like that. So the first state variable is regulator property. And then X2 is the bubble one, this one, starting with -1. It is also being regulated to 0. Fantastic result. And for that, you need to generate control signal, which is given in the star coded line, this one. Start with 4, high value, and goes down to 0. This is the optimal controls. So when this is happening, the P values, right, like P11 goes like this. This is where it starts. Eventually, it ends up somewhere here. Okay. And P12 and P21 is the bubbles and the stars, which is this one. They are on top of each other, two lines. Start somewhere here, stay flat, and then towards the end of the time, it goes like that. And the fourth p-value, P22, is this, goes like that. So you can see at the end, the p-values have, say, the last value is number 3. All of the other values end up at 1. So I think it was 1, 1, 1, 3, right? So finally, the values are there. Interestingly enough, you can see that the P matrix values stay flat for a long period of time. And only variation is towards the very end of the finite time. Right? So therefore, if you look at over here, even though we have a differential matrix equation, differential means there's a derivative, some sort of differentiation, dot, P dot. P dot is 0 for this part here, this part, and this part. So much of the time, you don't actually have differential matrix equation because P dot is 0 here, here, and here. Because we have fixed the time, we got this differential equation. If you had not fixed the time and let it go, right, we would get constant p-values. We get constant p-values without any changes. So which means p dots are 0. And all of a sudden, the differential matrix equation becomes algebraic matrix equation. There's no derivative, there's no dot. right? So we call it continuous algebraic Picard equation. Yeah. So which is very easy to deal with. You don't need MATLAB or anything to solve that Picard equation. You can manually solve it. But for that, you need to relax the time. It doesn't mean that you are taking big risk. You can simulate and figure out how long it takes to settle down. Now you have set 8 seconds. It regulates within 8 seconds. But if you let the constraint go away, infinite time linear quadratic regulator, you can simulate it and figure it out, how long it actually takes to uh, regulate the plant. With naturally the infinite time LQR, what if we relax the final time? There are a couple of things that happens when you relax the final time. Number one, your objective function becomes very concise like that. Now, you don't have to worry about the system dynamics as a constraint because system dynamics is anyway included in the process. If you look at the Ricardi equation, for example, right, it's already there, A and B. So we use the system dynamics as a restriction just in case, right, in finite time case, and to make sure that it's not violated, right, to give the perfect assurance. But in the finite time, anyway, it will not happen, any violation, right? Going away from system dynamics is not possible. And we are happy with the way it is in the Ricardi equation. So we can stick to this part only, right, as J. Second thing, the final cost can be dropped because when the system is given enough time, it will eventually reach zero, right? It will eventually reach zero because time is not restricted. So therefore, final state is zero. So final state cost is zero as well. Okay. Now, the third thing that will happen is that the metric Ricard equation will be equal to zero. E dot is zero. Remember earlier, it was like this, P dot, right, on the left-hand side. Now, you can keep the right-hand side intact because this has come from optimization process. On the left-hand side is the rate of change, and we set that to zero because there's no point of going back and deriving the whole thing again. This is just simply from transferring info from finite time to infinite time. So only the necessary changes are introduced. So this is our G running cost. There's no final cost because final state is zero. We assume that. And the algebraic differential matrix equation eventually becomes algebraic matrix equation, right? So manageable. And this is the rest is the same. LQR control as follows, right? You can have it. And because P uh, is coming from this one, you can actually calculate the values for P and you can put it over here. And this is your LQR control. Very easy. So when P dot is zero, which means P is a constant matrix. It's not changing. Earlier, in the finite time case, there was P dot. There was a rate of change. Because of that, P is different from 0 to T, F. That was one of the problems. You had to solve this first before you can calculate state vector, state trajectories, optimal controls, force state, etc. But now when P dot is 0, P is a constant matrix. You can immediately get it over here, right? R is a constant matrix, sorry, a value here for single input, single output. B is a constant vector. P is a constant matrix. Okay, so because these are all constants, this is the state, optimal state. This is the optimal controls. For each state, you can calculate the control signal. So before you can use this equation, you have to calculate x dot, x star, right? You first calculate P, then calculate x star, then calculate U star. Everything offline. This is still not a feedback. Okay, you can use this as a feedback once you design this one, right? You can simply plug it in there and get x star, calculate, and generate the control signal. So let's look at this example. X dot t equals 0, 1, minus 1, 2. Is this the same example? 0, 1, 1, 2. Yeah, same example, right? But it's good. This time, it's infinite time. You will understand, even though we say infinite time, whether we are actually going infinitely long, right? So this is our cost, same cost as of earlier, right? No change. Same initial state, no change. So this really, really comparable uh, uh, exercise, okay? Let's look at the solution. For this plant, cost function, uh, the following matrices have been determined in section 7.11, which is the earlier example actually. So this is A matrix, B matrix, Q matrix, and R. They all remain unchanged. The algebraic Ricard equation 722 with P1 to P21 is equal to P. These are off-diagonal elements. I just put P here, right? This is the matrix Ricard equation, algebraic Ricard equation. There's no P dot now. P dot is actually 0. So when you put A, B, R, Q into this Ricard equation, only variables are P, P11, and P22. Okay, you can do this computation eventually to get these three equations, right? One is for P, another one for P22, another one, actually three equations not separated with all these three variables. Now it's a simultaneous set of equations. You can solve them to find out the solutions. Actually, there are 4 solutions. Okay, this is the first one, second one, third one, fourth one. Right? Please do this manually yourself. Okay, these are the values for P and P22 and P11 from these 3 equations. Now, how do we select the one or many solutions out of the 4? If you look at the first one, right, if you make a matrix using these elements, you can see P11 is less than 0, right? P11 less than 0. It means P is not positive definite. So for a matrix to be positive definite, all principal minors should be positive. Principal minors are submatrices, square submatrices of the square matrix starting from the top left on the first element, first 2 by 2 matrix, first 3 by 3 matrix, like that, right? The principal minus. The first principal minus is the element at the top left corner, which is P11. When it is negative, we know for sure P matrix is not positive definite. So therefore, we remove it. This cannot be a solution, feasible solution. What about this one? P22 is negative. P22 means the last element, right? When it is negative, again, P cannot be positive definite. So we remove two solutions out. Then we are left with two middle solutions. We still don't know which one is the actual solution. Now you can generate using these two set of values for P, P11 and P22. You can generate two matrices, this one or this one. Okay. The second principal minors of the two matrices are, we look at second principal minor, which means the determinant of this one and determinant of this one. I am minus 2.5 and 13.151. So you can see the determinant negative, therefore this cannot be the solution. Finally, this one is the solution. Hence, the second matrix is the one that is positive definite. Okay, that's how we find out the constant P matrix here. Now, with the constant P matrix, we can define or synthesize our optimal controls, right? Using this equation. R inverse B transpose P is the linear quadratic vector. It is a set of gains. Control is set of numbers actually. Okay. When you have all the states coming in, you send it through this matrix and it generates the control signal. Say for example, if X is a two-state vector, right, two elements. So U is a single scalar, right? So you want to convert, you generate a single control signal using two state variables. Okay. So therefore, your control signal should be one row and two columns, right? One row and two columns. So now this is your what happened? Your R inverse. R is I think 0.5, so R inverse is 2. This is B transpose actually. This is the P matrix, right? When you have these things multiply, you get the single row, two element. It's a row vector. This is the linear quadratic regulator. Okay, finally it is 0.618, 3.288. Right? When you have the linear quadratic regulator, it's just two numbers. So much for getting these two numbers. Okay, then you can put it into your controller system. You have the plant, you have the output of the plant, two states. Uh, uh, it goes to the PID. This is PID, this is linear quadratic regulator. Of course, this is an experiment or simulation rather to compare PID controls with linear quadratic regulator. Because I think that it's important for us to know how good is linear quadratic regulator against very popular controller PID, right? So that's why this simulation. So the same plant, we get the two states, read from the state space model and send it to the quadratic regulator, which is this one. So what it does is it multiplies the first state variable with 0.618 and second state variable with 3.288. Add them together, change the sign, and put this as the control signal. Right? It goes on and on and on. On the right hand side, we have a PID controller designed in MATLAB using the MATLAB keywords given. And then use the state feedback. PID controller actually controls the plant, and we have the result. So here, MATLAB generates KP369 for this plant, KI820, and KD41. It's a fully fledged PID controller. These gains generate a huge control signal because very big gains. This is what MATLAB generates. Certainly not feasible for the control limit. So therefore, eventually PID gains were adjusted to KP8, KI8, and KD2, something like that. Both simulations start with the same initial condition 2 and -1. Okay, so when you compare the results, you will see something like this. The first state variable x1, okay, initial deflection was like 2, and both the controllers try to bring it down to 0 in this manner. You can see that the continuous line is LQR and a dash line is PID. Don't see much of a difference, right? But if you look at here, the control signal, this is the LQR control signal, this is the PID control signal. Even with the reduced gains, it goes very high up, right? So finally to achieve the same result. So I think PID consumes a lot of energy. It's not an optimal controller anyway, right? Even though in industries it's used, it costs a lot of energy, right, to get the same output. So you can see it here very, very clear. I think I have the MATLAB code written for that. LQR, which is fixed time. This is the finite time LQR. The same graphs I showed you earlier, right? So I think I don't need to read all these lines. You can understand. And this is infinite time controller. You can see MATLAB generates this controller, KP, KI, and KD, these values. Okay, so this is the result I showed. So I will share these codes with you. Please make sure you run it and figure it out, right? Understand it together with the theory.